Welcome to all. A new video on urban hydrology, the types of the stormwater runoff. Okay, in this video, we are going to learn about the different types of the stormwater runoff pattern in urban or suburban watersheds, or you can say the catchments. Okay, so yeah, so in hydrology, there are three major types of the stormwater runoff pattern you can observe. A variation from a small catchment to a large basin. Okay, so they are first one is the sheet flow, the second one is the shallow concentrated flow, the third one is the channel flow. Okay, based on the size of the catchment and its the magnitude, we can observe, or you can recommend either a sheet flow or shallow concentrated flow, or in combination of with the channel flow. Okay, so these are the three types of the stormwater runoff pattern we can observe. Okay, so in this part of the video we are going to learn about the what are the characteristics of these three types of the flow. Okay, and how it affects in the calculation of the TC, that is time of concentration. Okay, along with that we will also learn how it affects the hydrology of the catchment. Okay, and what type of the flow we should apply based on the catchment types and its magnitude and its condition. So these three things we will learn in this by the end of this video. Okay, so let's learn more into these stormwater runoff pattern with the help of flow charts, images, and the some empirical equation. Okay, so let's move into it. So I have brought you the slide with three pictures. So first one is the sheet flow. So let's understand more on the sheet flow. Okay, so you have came across, so whenever there is a beginning of the rainstorm. Okay, the water travels in the form of droplets. Okay, so that droplets form thin layer. Okay, that travels in a thin layer. You can see in the first picture on my left. Okay, so here you can see water is traveling in the form of thin layer. These thin layers are called as sheets. Okay, so this is sheet flow. Okay, regarding this depth, it is a less than zero point 0.1 feet, or you can say a 1 centimeter depth of water. It's a less than 1 centimeter depth of water. Okay, and it travels up to the distance of 150 feet max to max. Okay, because after traveling into the sheet flow for 150 feet, it gains some more depth, and at that time it get transition into the shallow concentrated flow. Okay, so if I can draw the water profile or the water surface profile of the sheet flow, so I'm using the pen tool and also change the ink color to blue. Okay, so here you can see, so I have drawn a line. So assume this as a ground surface of a land or a road. Okay, and this is a runoff traveling in the sheet flow in a thin layer. So sheet flow, it is traveling in a thin layer. Okay, and it travels up to distance of 150 feet. If I can put that 150 feet into the international standard units, that is in meter, that would be around 50 meters. Okay, so sheet flow, by that I can say that the sheet flow we can use to use this TC computation for the sheet flow for the smaller catchments. Okay, where the time of concentration is where the runoff water is traveling up to 50 meter or 150 feet. So by the in that case we can apply this sheet flow time of concentration. So in the next coming slide I'll discuss about the formula to compute the sheet flow. Okay, and the second one is the shallow concentrated flow. So in the shallow concentrated flow, the water is traveling in a certain path, certain fixed path, but but it doesn't have a well defined channel or fixed boundary. Okay, so if I can draw here, so um, suppose this is the ground. Okay, and this is the depth of the water. So it is not a defined, okay, it's not a well defined it doesn't have any well defined channels. Okay, and the shallow concentrated flow has a depth varying from zero point 0.1 to 0.5 feet. Okay, if I can put that into the international standard unit, so that would be up to the 15-minute depth the water, the runoff water is traveling in the shallow concentrated flow limit. Okay, and regarding its the range. Okay, it can, the shallow concentrated flow can travel up to the limit of 1,000 feet. Okay, so whenever the runoff water is traveling up to 1,000 feet after the sheet flow, means total 1,000 feet plus 50,000, sorry, 1,150 feet. In that case we can consider that. Okay, so if I can specifically segregate into the shallow concentrated flow, so it would be 1,000 feet. Okay, 1,000 feet if I can put into meters, so it would be around 300 meters. Okay, so in the international standard units. And regarding its depth, as I mentioned earlier, it is up to the 0.5 feet. Okay, 0.5 feet. If I can use the different ink for it, yeah. So this is a profile, water profile, water surface profile of a shallow concentrated flow, where the depth is slightly much higher than the sheet flow. Okay, so sheet flow it is up to less than 0.1, but for shallow concentrated flow it is up to 0.15, sorry, 0.5 feet or 15 centimeter. Okay, and the third one is the channel flow. So channel flow, you can observe these types of the storm runoff traveling in a well defined ditches or the streams. Where it has a fixed boundary where the water is channelized and traveling. Okay, you have seen this type of channel flow when finally the storm water runoff get discharged into swales or a stream. So in that case you can observe this channel flow, and it is clearly visible on the from the maps or aerial imagery. Okay, and if you compare the depth, it is the depth of flow in a channel flow condition is more than 0.15 feet. Okay, it is the depth of flow is much higher than sheet flow or the shallow concentrated flow in a channel flow condition. Okay, so especially for the shallow concentrated flow, we can apply that the combination of sheet plus shallow concentrated flow we can apply for a small when we have to compute this the time of concentration of the smaller catchments, say less than 5 acres of the plot or a land parcels, where we have to compute the TC. In that case, the traveling time for a catchment may vary from 100 meters to 300 meters. Okay, so in that case we can apply this combination of sheet plus shallow concentrated flow. In case of large watersheds or a basin, say 50 square kilometer of a big or a medium sized watershed, so in that case we have to apply the sheet flow plus shallow concentrated flow plus channel flow. Okay, so this is the initial cases of the sheet flow, concentrated flow, and the channel flow. Okay, in the next slide we will learn about the what are the calculation formula or the equation for the sheet flow, shallow concentrated flow, and channel flow. Okay, we will learn that in the next upcoming slide. um, let's understand the case of sheet flow, okay, with the help of example for which type of the catchment or arrangement we have to consider the sheet flow time of concentration or the travel time. Okay, this is very much useful when we are modeling these inlets or grades. Okay, so here you can see I brought you two pictures. Okay, so here in the first picture you can see the runoff water is rolling on the roads, okay, and forming a thin sheets while traveling to the lower elevation. So you can see the layers, that is called sheet of flow. Okay, same you can find in the below pictures. Okay, so as I mentioned in the previously, so sheet flow is applicable when the water is traveling, the runoff water is traveling up to the range of 150 feet or 100 or 30 meters, 150 feet or 50 meters. Okay, so this the sheet flow is very much useful in the modeling of the the inlets or the grades. Okay, you have seen the road grades or the curb openings to intercept these type of sheet flow runoff. Okay, and so here you can see on the I have drawn a small pictures to illustrate the how the sheet flow time of concentration we need to calculate. Okay, I'll draw with some other color. uh, yeah, okay, so here you can see this is a road. Okay, this is a road and this is a land which is adjacent to the road. Okay, this is a land parcel. Okay, and the third one is my the stormwater element, that is the inlet to intercept and convey this runoff from this road and land parcel to the main pipe conveyance or the channel conveyance system. Okay, so here the runoff from the roads and the land parcel both are intercepted, and this total length of travel of the rainwater or a runoff water is less than 50 meters or 150 feet. Okay, so in the next slide I will show you the formula to calculate the travel time of sheet flow. Okay, okay, so this is the formula to calculate the sheet flow travel time of the sheet flow. Okay, so where L is the length of the sheet flow, as I mentioned earlier, it is less than 150 feet. Okay, and the N is the Manning's overland roughness coefficient. So here you can have to consider the Manning's weighted Manning's roughness here in this case. So here it is traveling on the uh, partly on the road, which is asphaltic road, and partly on the land parcels. Okay, in that case we have to consider the weighted Manning's roughness coefficient. Okay, and along with that the next one is the P2. So P2 is the 2-year 24-hour rainfall depth, so which you can get it from the IDF. Okay, this is intensity duration frequency curve. okay, and the third one is the slope of the hydraulic grade line, okay, so that is approximately equals to the slope of the catchment, okay. So this is how we can calculate the sheet flow. The sheet flow, as I mentioned earlier, so sheet flow is very much useful to find the travel time of the inlets, small inlets, curb opening or inlet, so we have to consider this sheet flow, okay. So next comes the shallow concentrated flow, okay. This shallow concentrated flow, as I mentioned earlier, where the runoff is traveling at a depth less than zero point 0.5 feet or 15 centimeters. So you can see the tires of this vehicle or a car is partly inundated, okay, in the first picture, okay. In the second picture, so you can see overland flow which is draining to this channel on the ditches or a channel, you can see, okay. So if I use this pen tool to indicate and mark it, okay, so this is my shallow concentrated flow or overland flow which is traveling and reaching this channel. It's a perhaps it's a road channel, I believe. So you can see it has a visible depth of flow. This depth is more than uh, 15.5 feet or 15 centimeter, okay. So here this is a shallow concentrated flow and this is a channel flow, okay. So let's understand the formula to calculate the shallow concentrated flow, okay. So here is the formula. The first one, this is the formula where L is the flow length, okay, and V is the estimated velocity feet per second, okay. So this is the formula to calculate the shallow concentrated flow, okay. So this is shallow concentrated flow is applicable up to the range of this 1000 feet, or you can say 300 meters, okay. So here this can be very much applicable in the calculation of storm runoff from the land parcel for the development. So when we have to calculate the storm runoff development for a land parcel which is less than 5 acre or 10 acre land parcel where the development has to happen, so we have to calculate it, okay. So in that case, here there will be partly a sheet flow up to 150 feet, okay. There will be sheet flow, and thereafter the combination of shallow concentrated flow come into picture when the travel time of the runoff exceeds the 150 feet, and it will move into the shallow concentrated flow, that is 1000 feet, okay. Less than 1000 feet, in that case we have to apply the combination of shallow concentrated flow plus sheet flow, okay. And the third one is the channel flow, okay. The channel flow, you can see this it is visible in the road ditches or the swales, and it's also you can see in this large stormwater channel, you can see, or you can see city storm drain, you can see the channel flow. And this is the formula to calculate the travel time of the in case of channel flow runoff, okay. So this is derived from Manning's empirical equation to calculate this time of travel, okay. So where the n is the Manning's roughness coefficient for open channel, L is the length of travel, okay, and R is the hydraulic radius channel, okay, and S is the channel slope, okay. So this type of channel flow is also applied in the Musking and Kanch routing. For the river routing, we have to apply this channel flow, okay, when we are using this empirical formula to calculate the downstream hydrograph based on the upstream hydrograph, okay. This type of formula we have to apply it. Okay, and the this one is the time of concentration. Okay, the time of concentration mm, for a large basin. So if you want to calculate time of concentration for a large basin which is having a partly having the natural overland flow and stream flow, in that case we have to apply it in combination of sheet flow, shallow concentrated flow and the channel flow. Okay, in case of urban watershed where the development is proposed, in that case we have to apply for the sheet flow plus shallow concentrated flow. Okay, and the last slide is the picture which illustrates about the